Hello, my name is Shivania Naidoo. I am from the University of KwaZulu-Natal School of Chemistry and Physics. The title of my presentation is the proposed DFT study for the N-alkylation of amines via the borrowing hydrogen mechanism. Amines are an important class of compounds. They are found in natural products, in particular alkaloids. Amines are widely used in pharmaceuticals, agrochemicals, lubricants, and surfactants. The various transition metal catalytic systems developed for the N-alkylation of amines using alcohols are based on precious metals such as rhodium, ruthenium, palladium, and platinum. These metals have limitations and pose serious concerns, such as their high cost, limited availability, and toxicity. Hence, the focus has now shifted to developing earth-abundant transition metals, such as copper, nickel, iron, and cobalt, as catalysts for the N-alkylation of amines with alcohol. The borrowing hydrogen or hydrogen autotransfer mechanism shown on the left has become one of the most important strategies for the green and sustainable formation of the carbon-nitrogen bond directly from alcohols. The borrowing hydrogen or hydrogen autotransfer reaction is an environmentally friendly and atom-efficient reaction. Alcohol is the alkylating agent and water is the only byproduct. For my PhD, I will be looking at different earth-abundant metals. However, for this presentation, I will focus only on the borrowing hydrogen reaction for iron, which is shown in figure 1. The overall reaction is the transformation of an alcohol to the product amine. Since this is a catalytic process, there are 3 steps in which the transformation to the product occurs. Iron catalyst 1 is first activated in situ using trimethyl amine nitrogen oxide so that one of the carbon oxide is removed to give iron catalyst 1 oxygen, which has a vacant site. So in the dehydrogenation step, 1 hydride from the alcohol goes to the vacant site on the iron complex catalyst 1 oxygen, and the proton hydrogen from the alcohol group enone group, giving the iron catalyst 1 hydrogen. The product of step 1 is the carbonyl intermediate. In step 2, the carbonyl intermediate reacts with the amine to form an imine intermediate and water. In step 3, the borrowed hydrogen from the alcohol is used in the reduction of the imine intermediate to give the desired amine product. In the reduction step, iron hydride catalyst 1 hydrogen is converted back to catalyst 1 oxygen. The vacant coordination site is regenerated and the catalytic cycle closed. All the calculations will be carried out using Gaussian 16 and will be visualized in Gauss view. Gauss view will also be used to construct and modify the structures for the calculations. The computational details will be as follows. I will begin geometry optimizations using low-level DFT basis sets and functional. Then I will upgrade to higher basis sets and functionals to identify the best one for this reaction. During the calculations, especially when looking for transition states, it is possible that other intermediates may be present. So all mechanistic routes will be investigated. Once the gas phase optimizations are complete, the reaction will be modeled in the relevant solvent that was used experimentally. I will also attempt a comparison of suitable solvents. Finally, a reaction profile with the lowest free energy from the best mechanistic route and best solvent will be plotted. From the study, the mechanistic investigation will elucidate the role of steric and electronic parameters in the rate determining step. From literature, it states that the rate determining step can be both the imine formation as well as the imine reduction. We should be able to conclusively identify if step 2 or step 3 is rate determining. We also want to show that the reactivity of ion catalysts can be controlled using the borrowing hydrogen mechanism, which will enable the discovery of a range of other new catalyst structures and sustainable transformations using abundant iron. I would like to acknowledge the University of KwaZulu-Natal for accepting me as a part-time PhD student, the NRF for funding, and the CHPC for computational resources. Thank you for your time and for listening.